Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So what we are going to be doing today in section 4.3 is taking another bite at an old apple, and that has to do with linearly independent sets and bases. Only now, as usual, in our second visiting of this topic, we'll be broadening our horizons a little bit. So linearly independent sets. And bases. So bases is a plural of basis. And as for linearly independent sets, hopefully by now that speaks for itself. Alright, so let's start with what is called the spanning set theorem. Alright, so here's the setup here. We're going to have a set. That set is going to be S, which equals a collection of vectors v1 up to vp. And we're going to have another set, H, which is going to be the span of S. So in other words, the span of the v1 up to the vp. Now, here now is the spanning set theorem. So if any of the vi, so in other words, any one of the v's, is a linear combination of the others, then removing it won't change the span. So in particular, if I want to put that into the notation from above, let's say that S tilde is equal to v1 up to vi minus 1. So in other words, all of them up to the offending number. Then we skip vi. So this is S take away vi is what this means. So this, by the way, is also legitimate terminology. You can say set minus is how you pronounce that. So this, then span of S tilde will be the same as the span of S. So that's what it would look like in math slang. But the important thing is deleting an element that is linearly dependent on the others will not change the span. Now B is a little bit more meaty. So if H is not just the set consisting of the zero vector, in other words, if S is not just the zero vector, then some subset of S forms a basis. for H. And recall what it means to be a basis, i.e. is linearly independent but still spans H. Now, what this effectively means is we can, one by one, whittle away all of the elements of the spanning set until we have only linearly independent ones left. And once we have done so, we can reduce it down to a basis. So that's what it's saying here, is that you can, one by one, remove all linearly dependent elements and are left until you're left with only the linearly independent ones, but which nonetheless still span the space. Now, as a follow-up to that is the following note. Any dimension n subspace of Rn must actually be all of Rn. So if you have a subspace of a finite dimensional vector space Rn and your subspace has dimension n, then that means it must actually be the whole thing. So what this means is, so thus, any collection of n linearly independent vectors in Rn must actually form a basis for all of Rn. So if we have any collection of n linearly independent vectors in Rn, then those will be those will span some set H. Now, if they are linearly independent, that means they will actually form a basis for H. But if H has a basis with n elements, that means by definition that it's n-dimensional. And if it's n-dimensional, then that means that it must be, in fact, the entirety of Rn. So what this is saying is there is no two-dimensional subspace of R2. So the plane basically has the following subspaces: the origin, which is the zero-dimensional, a line through the origin, which is the one-dimensional, and then the whole plane. There's nothing in between, is what this means. So, for example, therefore, R2 only has the following subspaces. So these are the subspaces. We listed them before, but now we know, in fact, they are the only subspaces. So dimension 0, that's the origin. It's the only vector space that doesn't have a basis. Dimension 1, a line through the origin. And then dimension 2, the whole xy plane. So there is no space in between those. No vector space in between those that satisfies the three properties of a vector space. So, i.e., there is no vector space in between. In between these. So, henceforward, if you are ever asked whether, for example, quadrant 1 is a vector subspace of R2, the fact that it is more than a line but less than the whole plane automatically gives you a thumbs down. It could not be a vector space. Vector spaces only come in these categories. And the same thing is true of R3. So if we're talking about R3, the vector subspaces of that will be the point at the origin for the zero-dimensional, a line through the origin for one-dimensional, a plane through the origin for two-dimensional, and then all of R3, but nothing in between. Alright, so let's take an example here. Does the following. Form a basis for all of R3. And the following will first consist of the following set. Let's say this set here, the set 1, 0, 1, and then 0, 0, 0, and then 0, 1, 0. Alright, well, as soon as I wrote that second one, already you probably were pulling the in case of emergency lever here. We have got a case closed ironclad decision on this. The verdict is, it is not. These are three vectors, but they are not linearly independent. So they are not linearly independent. And that's because of the 0, 0, 0. And so it's not a basis. So to be linearly independent and yet span the whole space, that's what it takes to be a basis. This does not accomplish that. Alright, so now how about this set? So we are going to take another set of three vectors, and it will be up to us to determine whether this set of vectors in fact is a basis for R3. So let's go with the vectors 1, 1, 1, and then the vectors 0, 2, 2, and then the vector 0, 0, 3. Now, looking at this, if we were to make the matrix A out of the columns or whose columns are these vectors, we'd have 1, 1, 1, 0, 2, 2, 0, 0, 3. And we can actually tell all kinds of things about this from any of our various theorems, such as if we were interested in the determinant of A, we could tell that it is not 0 because this is a triangular matrix, a lower triangular matrix. And so we know that its determinant is not 0, and therefore the columns are linearly independent. Similarly, we can use any other piece of the invertible matrix theorem, such as A transpose. would then be upper triangular, which would mean that it has a pivot in every column. So the columns are linearly independent for a number of reasons, but for one thing, we can tell its determinant is not 0, and so we'll just say that because it's easy. And the determinant being or not being 0 is completely equivalent to any other of the invertible matrix theorem conditions. So, case closed. So this means we have 3 linearly independent vectors, which therefore do form a basis for R3. So the set is. The set is a basis for R3. Okay, now there's another twist on the same sort of thing that we've been doing as far as column and null spaces that we can also apply for a slightly different setup. So other kinds. Of subspace. So, given a subspace defined by an equation, we can attempt to find a basis by changing the equation into a matrix and analyzing the null space. So for example, a classic example of something like this would be a plane in R3. So we could take, so this is an example, a plane in R3. We could take something like this. Find a basis for the plane, and the plane could be x plus y plus z equals 0. Alright, so if we want a basis for this two-dimensional subspace, we can just think of this as the augmented matrix equation 1, 1, 1, augment 0. So then the null space here, we would row reduce this as much as we could, and here it already actually is row reduced. So that means that y and z are free variables, and we could have x, I guess I should write it x plus y plus z equals 0, which means that x equals negative y minus z, y equals y, z equals z. And then if I wanted to try to express this as a vector, it would be x, y, z is equal to, and then you could just go with free variable y times -1, 1, 0 plus free variable z times -1, 0, 1, which means then a basis for the null space, so let's call this A. So then the null space for A will have basis, and it'll be these two vectors. -1, -1, 1, 0, and -1, 0, 1. Now, this is a task actually that is very similar to the task that you might have done in Math 254, in which you wanted to find the parametric representation of this plane. So the parametric representation of this plane, one version of it would be just like a u times this plus v times that. So you have so you can have a parametric representation of a plane, which is the same task as finding a basis for the null space, which means a basis for this subspace. So what that means is all the points that are on this plane will be some linear combination of this vector and that vector. Alright. But anyway, that will do it for this section. So join me for the next episode of Math 261, in which we will discuss bases and coordinate systems. So till then, bye.